Let us discuss one-dimensional heat flow equations. Here we shall consider the flow of heat and accompanying of temperature with position and time in conducting solids. The following empirical laws are taken as the basis of investigation. So we'll have to use these two laws. Heat flows from high temperature to low temperature. Of course, heat will flow from high temperature to low temperature. The second one is the amount of heat required to produce a given temperature change in a body is proportional to the mass of the body and to the temperature. So which is proportional to mass of the body and the temperature. This constant of proportionality is known as specific heat capacity of the conducting material. The rate at which the heat flows through an area is proportional to the area and to the temperature gradient. So temperature gradient is nothing but you have dt by dx, and this constant of proportionality is known as thermal conductivity K, so which you have already studied earlier in thermal physics. Consider a bar. You just take a bar or rod of homogeneous material, and density is given by rho and cross section is given by capital A. We suppose that sides of the bar are insulated. Just consider sides of the bar are insulated, and the loss of heat from the sides by conduction or radiations are negligible. We are going to neglect conduction and radiation. And of course, there are two cross sections here. You have two cross sections of area. We have one is this one, B F E D B. Then another one is L P N M L. And this goes from 0 to x, and this goes from 0 to x plus dx. So we have x plus dx, and this is nothing but your x. Taken the end of the bar as the origin and the direction of the heat flow as the positive x-axis. Okay. Let C be the specific heat and K be the thermal conductivity of the material. Now consider two, as I said, two parallel sections of cross sections of area lying from 0 to x and lying from 0 to x plus dx. Okay. The section is perpendicular to the x-axis. The mass of the element is given by A rho del x, and we know that rho equals mass by volume. Okay, density equal to mass by volume. We need to have mass. So mass equal to density multiplied by volume. So you have density multiplied by A del x is our volume. A del x. A is the area. Del x is a small length. So A times del x will give you volume. So volume multiplied by density will give you mass. Let U of x comma t be the temperature at distance x at time t. By the second law, which you have already stated, the rate of increase of heat in the element is given by this, which is proportional to the mass and gradient. Mass and gradient. Mass is given by this, gradient is given by this. So we have A rho del x C times du by dx. Now let R1, R2 are respectively the rates in terms of calories per second of inflow and outflow for the sections x equal to x and x equal to x plus del x. So your R1 equal to minus k du by dx at x, and R2 equal to minus k times du by dx at x equal to x plus del x. There are two sections. The negative sign being due to the fact that heat flows from higher temperature to low temperature, du by dx is negative. So equating the rates of increase of heat from the two empirical laws, we have this expression. So we have this expression which is equal to R1 minus R2. You just substitute the expression for your R1, substitute the expression for your R2. So this is expression for your R1. This is expression for your R2. So R1 minus R2, that will give you this. You bring this term to left hand side. So that will give you this one, K and K, A and A will get cancelled. K divided by your rho C is here. Del x is here. Is it okay? I can bring all the terms, this term to right hand side. And A will get cancelled. Other things and all let it be K by rho C. So we have this term. Now when del x tends to 0, x plus del x equal to x, substitute here, we have K divided by rho C d by dx partial du by dx, which is equal to du by dt. So we have du by dt equal to k by rho c d squared u by dx squared, and this equation is nothing but one dimensional heat flow equation, heat flow wave equation. In ordinary wave equation, sound equation, can you remember? We have two partial differentials in the second order, but this time single order, and this is your second order differential equation. Single order differential equation. This is second order differential equation. In the earlier case of wave equation, we had both second order differential equation. So you have to differentiate these two. So now by method of separation of variables, we are going to solve heat flow equation, which is nothing but du by dt equal to c squared d squared u by dx squared. So we are going to solve using method of separation of variables. So as usual, e of x comma t equal to x of x t of t. Okay. Now here it is given as du by dt. You have to differentiate only one time with respect to t. You have to differentiate two times with respect to x. Correct. So you have to differentiate this because only once du by dt. So that will give me du by dt. Differentiating this one will give me d by dt times xt, keeping x as constant. So that will give me x dt by dt. So instead of this, we can substitute this. Okay. Now we will go for this. We will have to differentiate two times. So we have now du by dx equal to c squared times d by dx xt. So we will have to differentiate two times. That will give me c squared t dx by dx, c squared t dx d squared x by dx squared. So we have differentiated two times. Is it okay? So instead of this, you can substitute this. Instead of this, you can substitute this. Is it okay? See, instead of this, you can substitute this. Instead of this, you can substitute this. So substituting will give us this. Now separating the variables. As usual, the same technique, separating the variables, that will give me 1 divided by c squared t dt by dt equal to 1 by x d squared x by dx squared. Look at this equation. On left hand side we have t variable, right hand side we have x variable. So we have separated. This is equal to, this must be equal to some constant, which is nothing but minus b squared. We are going to keep this as minus b squared. So your right hand side. So right hand side, which is nothing but 1 by x d squared x by dx squared equal to minus b squared. Okay, we can solve easily. This is second order differential equation with a single variable, so you can solve. So which is equal to minus b squared. Now we are going to solve separately. So 1 by c squared t dt by dt equal to minus b squared. I can bring this. I can take this c squared that side. I can take this dt that side. So that will give me dt by t, which is equal to minus p squared c squared dt. Integrating on both sides will give me log t p2ct t plus c1. Integration constant is c1. Raising to the power exponential, that will give me t of t equal to c1 e to the power minus p squared c squared t. Similarly, we have another equation and differential equation that will give us d squared x equal to minus p squared x. Your auxiliary equation is p squared minus p squared, and m equal to m squared equal to minus p squared. So m equal to plus or minus ip. The solution of this auxiliary equation is given by this. Product of these two will give me complete solution. The same technique. So product of these two will give me a complete solution, and e of x comma t equal to, this is t of t and this is x of x. So that will give me complete solution. Okay. So very simple method. Now find the temperature in a bar of length 2 whose ends kept at 0 and lateral surface insulated if the temperature is given by this. So this is your f of x. This is for f of x. Length of bar is given as 2. Okay. And ends kept at 0. We'll see. Now we'll have to use only heat flow equation, one dimensional heat flow equation. Partial du by dt equal to c squared d squared u by dx squared. And solution of this differential equation, partial differential equation, is given by this. We have already obtained. So we have already obtained. So I have used. Is it okay? The thing is, we'll have to use method of separation of variable. We'll have to differentiate two times, substitute here and integrate, separate the variables and integrate and get the solution of x of x, get the solution of t of t, product of these two will give you this complete solution. So that's the idea. Now what is given here? Putting x equal to 0 is u equal to 0. This is one condition. Okay, whose n's kept at 0. So x equal to 0 means u equal to 0. You substitute here x equal to 0. When x equal to 0, sin 0 is 0, cos 0 is 1. So we have c1 times c3 e power minus p squared c squared t. Okay, so this is equal to 0, u equal to 0, it is given. So c1 c3 e power minus p squared c squared t. So we are going to imply that c1 equal to 0. So substitute c1 equal to 0 in equation 1. So this one will go up. We have c2 times c3 sin px e power minus p squared c squared t. Now yes, is given in the problem. See, in a bar of length 2 it is given. So bar of 2, x equal to 2. So instead of x you substitute 2 here. So that will give us 0, which is equal to c2 c3 sin 2p e power minus p squared c squared t. So it implies that sin 2p equal to 0. So the condition goes like this: sin n pi equal to 0. So we can get the value of p equal to n pi by 2. See, sin 2p equal to 0, which is equal to sin n pi. Sin n pi equal to 0. So it implies that p equal to n pi by 2. N is an integer. N equals 1, 2, 3 goes on. Okay. Now substitute the value of p. P equals n pi by 2, and of course we know the expression u equal to c2 c3 sin px e power minus p squared c squared t. You substitute the expression for p here, you will have complete solution. Okay, and I have written c2 c3 I have written as bn. So this becomes v of x comma t, which is equal to bn times sin n pi x by 2. See, sin n pi x by 2 e power, instead of p squared you have to substitute n squared pi squared by 4. See, n squared pi squared by 4 c squared times t. Now this is a general solution. General solution is given as n, as we discussed, n is an integer, goes from 1 to infinity. So 1 to infinity, summation over n equals 1 to infinity bn sin n pi x by 2 e power this expression e to the power minus n squared pi squared c squared t divided by 4. Now putting t here, t equal to 0 here, you just substitute t equal to 0, which is equal to u as it is given. See, as I said, f of x. Can you remember? This is nothing but u of x comma t. Okay, so but here u of x comma t, as I said, but t is not there. So it depends only on x. This is your f of x, and the solution is nothing but u of x comma t, and this must be your x, u of x comma t, but t is not there. So t must be 0 here. So that's why u of x comma 0. See here, substituting t equal to 0, that will give us this expression. So this becomes 1. So we have now bn sin n pi x by 2 this side, and left hand side you have sin pi x by 2 plus 3 sin pi by x. It is given in the problem. You will expand this b1, b2, b3. You substitute for n equal to 1, 2, 3. When n equal to 1, we have b1 sin n pi x by 2. When n equal to 2, we have this dot dot dot. We go for b5. b5 equal to sin pi x by 2. You compare the coefficients now, left hand side, right hand side. We have now, see here, this is your sin pi by 2, equal 5 by 2. Here it is pi by x by 2, so pi by x by 2. You can get the value of b1 and b5. See, b1 is nothing but your 1, and b5 is nothing but your 3. See, you can compare. I repeat, you substitute for n equal to 1, 2, 3 goes on. So we have now n equal to 1, b1, n equal to 2, we have b2, n equal to 5, we have b5. You compare this one and this one, that will give you b1 equal to 1, b5 equal to 3. You have found out the expression for b1 and b3. So b1 equal to 1, b5 equal to 3. You substitute here. That will give us u of x comma t will give you sin pi x by 2 e to the power minus n squared pi squared c squared t by 4 plus 3 sin pi by x by 2 e power minus pi squared c squared t by 4. Now let us solve the last problem. Solve the equation du by dt equal to d squared u by dx squared with the following boundary conditions. So following boundary conditions are given. U of x comma 0 which is equal to 3 sin n pi x. Another boundary conditions given as u of 0 comma t, u of L comma t equal to 0. So we have this condition. So t equal to 0 here and x equal to 0 here, here x equal to L. Is it okay? See, u depends on x comma t. So u depends on x comma t. U is a function of x comma t. T is 0. So this is one condition. Then another condition is x is equal to 0. Then another condition is x equal to L. Okay? So now the equation is given as du by dt equal to d squared u by dx squared. Its solution is given by this. So we know already the solution we have obtained earlier using method of separation of variable. So now putting x equal to 0 here, x equal to 0. So x equal to 0, u equal to 0. So this is the equation that we have obtained. Putting x equal to 0 in this equation, that will give me c2 plus 0 times this one. So we have c1 c2 e power minus p square t. It implies that c2 equal to 0. Substitute here. So that will give me u equal to c1 c3 e power minus p square t sin px. Is it okay? I repeat, you just substitute x equal to 0 here. We will have this one. It implies that c2 equal to 0. You substitute c2 equal to 0 here. This one will go off. You have this alone. This multiplied by this will give you this. Now, second boundary condition. See here, x equal to L. So we will have to substitute wherever you find x equal to L here and u equal to 0. So 0 equal to wherever you find x. So it implies that c2 already is 0. So we have now only this alone. So we have now c1 c3 e power minus p square t sin pl. So wherever you find x, you substitute L. So sin pl equal to 0, which is equal to sin n pi. 0 equal to sin n pi. So pl equal to n pi. P equal to n pi by L. So we have the expression for p. So we can substitute for p. Putting the value of p in equation 2. So this is equation 2. So you substitute p equals n pi by L. So that will give me u of x comma t equal to c1 c3 e power minus p squared is nothing but n squared pi squared by L squared. So n squared pi squared by L squared. There's a mistake here. This is L squared. Okay. Sin n pi x by L, which is equal to c1 c3. I can write this as bn. So bn e times minus n squared pi squared t by L squared. Sin n pi x by L. Okay. So now I can expand this one. So n equal to 1 to infinity. So bn e power minus n squared pi squared t by L squared sin n pi x by L. So this is our general solution. Now it is given us in the problem. It is given us, see, u of x comma 0 equal to 3 sin n pi x. It is given as the problem. So we will have to use when t equal to 0, u equal to 3 sin n pi x. So 3 sin n pi x equal to, wherever you find t, you just substitute 0. So e power 0 is 1. So we have bn alone. This term, let it be like this. Now you will have to expand this one. You will have to expand. When you are going to expand, this becomes b1 sin 1 pi x by L plus b2 sin 2 pi x by L, correct, plus 3 sin 3n pi x by L. You compare these two. So your b3 becomes 3, L equals 1. You will have to expand in terms of n equal to 1, 2, 3 and compare the coefficients. We will have bn equal to 3, L equal to 1. So substitute in this expression. So we have now p of x comma t equal to, we have already found out b3. So which is nothing but bn is nothing but 3. So we have 3 times summation over n equal to 1 to infinity e power minus n squared pi squared t sin n pi x. So that's the solution. Now a rod of length L with insulated sides is initially at a uniform temperature. Its ends are suddenly cooled at 0 degrees C. So this is the condition and are kept at that same temperature. Prove the temperature function of U of x comma t is given by this. Prove that the temperature function is given by this. So we have got to prove this, where Dn is determined by this equation. Let the heat flow along a bar of uniform cross section in the direction perpendicular to the cross section. Take one end of a bar as the origin and the direction of the heat flow is along the x-axis. Okay, let the temperature of the bar at any time t at a point x distance from the origin be U of x comma t, and we know the heat flow equation is given by this. So we know already. Now we have to use separation of variable technique. U of x comma t equal to x of x t of t. We can differentiate once with respect to t. We can differentiate 2 times with respect to x. Will give us this. This is separated as x and that is separated as t. So we can use separation of variable technique and we can use some constant. Okay. See, we have now. I can bring this c square t this side. I can take this x to the right hand side. So that will give me 1 by c square t times dt by dt equal to 1 by x times d square dx by dx square, and we have separated the constant, we have separated the variables. So this must be equal to some constant which is equal to minus p square. So we have 1 by c square t dt by dt equal to minus p square, and 1 by x d square dx by dx square equal to minus p square. Okay, is it okay? So now I can take this side, c square t term to that side. So that will give me dt by dt equal to minus p square c square t. I can bring that term to left hand side, that will give me this. So this is your auxiliary equation. D square plus p square c square t equal to 0 will be your auxiliary equation. Similarly for x variable we have d square dx by dx square, which is nothing but d square. So d square plus p square x equal to 0 is an auxiliary equation. So this is your auxiliary equation. So d plus p square c square t equal to 0, that will give me this. So m equals minus p square c square, and solution of this differential equation is given by this. Similarly, the auxiliary equation for the variable x is given by this. Solution of this differential equation is given by this. Product of these two will give me the complete solution as usual. So we have the product that will give me the complete solution. Now conditions given there, when x equal to 0, u equal to 0. You substitute in this expression. Okay, x equal to 0, u equal to 0. X equal to 0 implies that c2 times 1. This becomes 0. So c2 times 1. So that will become c1 c2 e power minus p square c square t. Okay, it implies that c2 equal to 0. c1 cannot be equal to 0. Suppose if c2 equal to 0, then this will not be there. This term alone will be there. So we have v of x comma t, which is equal to c1 e power minus p square c square t times c3 sin px. So this is one boundary condition we have used. Another boundary condition is x equal to L, u equal to 0. So wherever you find x equal to L, you will have to substitute x equal to L. You will have to, wherever you find x, substitute L. So that will give us 0 c1 times e power minus p square c square t c3 sin pl. It implies that sin pl equal to 0. As usual, sin n pi, so your p equal to n pi by L. Wherever you find p, you substitute n pi by L, where n is an integer. So u equal to, so this is we have obtained. Wherever you find p, you substitute n pi by L. So that will give me c1 c3 e power minus n square pi square c square t by L square, so sin n pi x by L. And of course c1 c3 equal to b1. So this equation becomes exactly like this. Suppose we are going for a general solution. So n equal to 1, 2, 3, where n is an integer, then the most general solution will be this. Summation over n equal to 1 to infinity b1 e power minus n squared pi squared c squared t divided by L squared times sin n pi x by L. Your bn is given by this. Your bn equal to 2 by L u naught. This is your f of x sin n pi x by L dx. Okay, now it is you will have to just integrate. When you are going to integrate, you can find out the expression for your bn. Integrate this one with respect to x. So 2 by L, you pull u naught out. Integrating this will give me this minus cos n pi x by L divided by n pi by L. I have written minus L by n pi cos n pi x by L. You have to substitute the upper limit minus you have to substitute the lower limit. So substitute the upper limit, that will give me, upper limit will give me n pi L, that by L, then L will get cancelled, we have n pi alone. Sin 0 is, sin 0 I have written, sorry, cos 0 is I have written as cos 0. So we have cos n pi minus cos 0. I repeat, see here minus L by n pi. You substitute the upper limit. Cos n pi L by L. L will cancel. Cos n pi minus cos 0. So minus cos 0. Cos n pi is minus 1 to the power n. Correct? Cos n pi. Cos pi is minus 1. Cos n pi is minus 1 to the power n. Cos 0 is 1. So I written as minus 1. I can pull this minus, I can keep this minus n inside. So that will give me 1 minus minus 1 to the power n. Correct? I can multiply this minus n inside. So that will give me 2 u naught by n pi 1 minus minus 1 to the power n. So when n equal to odd or when equal to even, suppose when n equal to 0, this becomes 1 minus 1, 0. When n equal to 2, again 1 minus 1, 0. For all n equal to even, n equal to 0, 2, 3, 4, answer is 0. When n equal to odd number, 1, 3, 5, when n equal to 1, that will give me 1. 1 minus of minus 1. So 1 plus 1, 2. Already 2 is there. So 4 times u naught by n pi. So where n is odd, you will have this expression. When n is even, you will have 0. So your complete solution will be e of x comma t equal to 4 u naught by pi, 4 u naught by pi, 4 u naught by pi. I have written n inside because summation over n equal to 1 to infinity. But for all even number it is 0, so only it exists only for the odd numbers. So 1, 3, 5. So 1 divided by n. See here I have kept it 1 by n. Complete solution will be sin n pi x by L e times minus n squared pi squared c squared times t divided by L squared. So instead of n you substitute 2n minus 1 and you can remove n equal to 1. N equal to 1, 3, 5 you just remove. Wherever you find n, you substitute 2n minus 1. So that is the complete solution. So the complete solution is given by this expression. So that is the end of this mathematical physics. Thank you for your cooperation, students. So thank you. Bye.